continuation today of our meeting on the gas turbine emission control. And we're now going to be hearing from our fifth speaker, Don Wyatt of Yokogawa. And Don is the global sales manager on the Yokogawa Laser Analysis Division and has a career starting back with Fisher Rosemont in 1944 to 6. And then with Analytical Specialties, which is a company that maybe he'll tell us a little bit about too, that has specialized in the TDL and was attractive enough to that Yokogawa acquired him in 2008. And as you can see, he has been sales manager, vice president for 3 years of the Analytical Specialties group. So with all that background, Don, let's move on to your actual presentation. So I'm going to X this out right here. And we'll get the presentation, put that into the mode here, and Don, we're ready to go.
Okay, well, thanks, Bob. Thanks for your time today. I really do appreciate it. I'll just start here with a little history, because I don't have slides on it, where this particular product was developed. Back in about 2003, Analytical Specialties, we actually, along with the help of Dow Chemical, we realized there was a gap in measurement techniques, and there were existing tunable diode lasers on the market, and they actually, were probably in use since the mid '80s for certain applications. And what we realized is that there was a gap in that technology, and Dow actually brought that to our attention, and they wanted to see some better background rejection, better accuracies than what they'd seen in previous models. So they basically came to Analytical Specialties, and we were a small company here on the Gulf Coast of Texas, providing analyzer technology basically as a manufacturer's rep firm, and but we provided lots of solutions to Dow Chemical, and when they decided that they wanted to see enhancements in the technology, we worked with Dow as our industrial partner. We were the commercial partner, and then they actually worked with the Department of Energy, basically from a point of view of reducing energy costs. So we actually did 2 Department of Energy grants, and they're listed in my bio, that we worked on to actually develop this particular product line from a TDL basis to basically to give you enhancements over what was out there in the field. It was mainly focused on combustion technology, measuring oxygen, CO, methane in the radiant section of fired heaters, gas. We've even done some coal as well. And then it rolls over into the power industry from a combustion point of view. But one of the measurements we can make, we'll talk about today, is actually the low level of ammonia directly in the process using this absorption spectroscopy provided by commercially available tunable diode lasers. Okay, next please. Yeah, that's fine. Right there's good. That's all right. Background. Basically, section 1, we're going to talk about what are we trying to do? What is the application, and what are the benefits? Okay. So this particular discussion is basically where we're focusing on gas-fired applications, both gas-fired boilers and also gas turbines. We actually can have had some success measuring ammonia slip in coal-fired boilers as well, but we'll talk about gas today. This just basically shows the difference between a gas-fired boiler, the conditions, whereas in a boiler, basically the temperatures of the outlet gas are 800 degrees Fahrenheit typically. When you move to a turbine, the temperatures are much higher coming out of the turbine itself. And an interesting note here about the amount of NOx coming out of the 2 different types. Gas turbines have half the amount of NOx usually that you see out of a utility boiler. Okay, Bob, next. And we have had some success at measuring in both gas boilers and gas turbines. Not some success, we've had success in every installation that we've installed. The difference is, like I said earlier, we have temperature. There's higher temperatures. Sometimes in gas turbines, we have to be very careful of when we start. I'll show you where we make the measurements, but being able to actually find a place to shoot the beam through the exit gas after the SCR. But the gas turbine and the gas-fired boilers, they actually have different things that we have to look at as far as the measurement is concerned: the temperature, geometry, and then sometimes the level of NOx or ammonia coming out. Okay, next. So when we look at a system, and this shows a diagram of a gas-fired boiler, not really a turbine, but there are commonalities here. And I'll explain in a moment, but there's two main types of NOx reduction systems that we look at. The most common that I've seen out in the field is SCR, where there's a catalyst that's used where the flue gas runs through the catalyst, ammonia of some either aqueous ammonia or gas ammonia is injected in the flue gas, runs over the catalyst, the NOx is reduced. And then you don't see both of them in the same application. This shows that both SNCR and SCR show you where the injection points are, but in SNCR you would see the ammonia injected directly into the flue gas with no catalyst, and the residence time in the system allows for mixing of the ammonia reagent and the NOx in the flue gas to reduce the NOx. Advance forward one for me, Bob. Okay. One more time. So what has popped up here is after the back pass, in between the back pass and then the SCR, there is the TDLS 200 TruePeak is shown right here. And actually, in this first analyzer that they show here on the far left, you would see that installed in an SNCR application where there's no catalyst, where we're measuring the ammonia slip coming after the mixing has occurred. And we typically see higher level ammonia levels on SNCR than we do in SCR as far as the slip is concerned. In fact, we have seen as high as 10 to 15 ppm on SNCRs. And if you move to the TDLS that's shown here in the middle of the page after the SCR, this is more typical of gas-fired or even coal-fired systems where we're actually looking at the ammonia measurement after the SCR to make sure that the slip is within the required levels for the catalyst manufacturer, and then also make sure that we have the right amount for emissions as well. In some cases, we've actually installed the TDL ammonia analyzer in the stack for regulatory purposes. Some states, such as I know we did in Delaware and California, and actually in Houston and Texas, we've had TDL put as far as for outlet measurements for regulatory compliance. And you have to make sure that it's permitted correctly so that you can do the validation of the analyzer correctly. Since it's an in situ measurement, there's no way to isolate the measurement to do a zero calibration or validation. So we have to do some standard addition to be able to validate. And if the state accepts that, and we've had that accepted in several states, you can use that actually for a regulatory measurement as well. Okay, Bob, let's move forward.
Before we do that, I just wanted to clarify, when you said you're having the analyzers in the stack, would that be for CO2 and for CO and so forth, or is that for the, or were you directing that direct to the NH3?
Today it's specifically for ammonia, and it's a state-by-state permit acceptance. You have to go get the permit updated to be able to do this in situ wet measurement. Now, one thing I didn't mention, Bob, is that we have, in some cases, this analyzer can also measure the moisture in the system. So if the state would require you to provide a dry measurement, we can actually measure both the ammonia and the moisture at this point, and the analyzer can actually output dry ammonia.
Which I think is an important, you know, you and I were talking to a customer who was saying how important that was in terms of meeting the regulatory requirements.
Correct. Yeah, so today, to answer the question you actually asked, I apologize. For the CO and the CO2, yes, we can make those measurements, But traditionally, with the standard regulations, since everything is basically has to be reported as dry, today most people will not accept those cross stack for two reasons. They're wet, which we can actually correct for by measuring the moisture, but there is no way to do that zero validation calibration because the process is always in the beam. So that would be a philosophical change in the way that our regulatory agencies do things today. Not to say that it couldn't happen.
Now, in terms of actual installations, too, you've got a big installation at AEP Clinch River on an SNCR for a coal plant. So
correct, and that you're right. That's actually twofold. You're right, and that is actually in the center installation after the it's after the SNCR, and it's actually to make sure that we have the right stoichiometric mix for the ammonia and the NOx, and also for regulatory purposes. But it is actually not at the stack. It's actually down there in the closer to the boiler.
I see. Okay.
Okay. Yeah, you just keep going forward. That's fine.
Yeah, I see. Okay.
I have to thank Ed Deck for this presentation.
Yeah, that's interesting. There we go.
So, all right, next is fine. We'll talk about some of the pros and cons here. So, as mentioned earlier in some of the presentations, there are multiple sources for ammonia. You can use, I don't know if anybody uses ammonia gas, but it's available. Most are urea or liquid-based aqueous. And it's fairly, the main reactions are fairly simple. Ammonia is present at the temperature. With or without catalyst, you're going to have all the NO and NO2 basically go to nitrogen and moisture or water. It just depends on at what temperature and how much ammonia is required, depending on which system that you use. And there were some mentions earlier today about safety, using the aqueous versus gas. So to us, it doesn't really matter from a measurement point of view. When it hits the temperature and it goes into the mixture, it's going to basically go to ammonia. Whatever is not reacted is going to turn to ammonia, and we'll be able to make that measurement. Okay, next, please. Here's just a picture to give us an idea of what we're actually physically looking at. And whether you have gas-fired or coal, and even in some gas turbines, you're going to see SCRs, where you basically have a system set up that's filled with catalyst where the flue gas is running through. And if we look, so that's what you see up here on the top right-hand picture or graphic. That's going to be what the SCR looks like, or it is a version of an SCR. If we go straight down the page, you see what the new catalyst looks like, and it's a honeycomb where the flue gas is going to flow through and make contact and mix with the ammonia, and this allows us to get good mixing of the flue gas and the ammonia, so that, and then we would actually measure the slip coming out of here to make sure that the system is behaving properly, and if you're interested in emissions, we have that number as well. And the picture here on the bottom left is basically just giving an idea of what the nozzles look like that you're injecting the reagent through, and then often they'll mix air with that as well. And then we'll be downstream of this to make the measurement. Next, Bob. So another depiction of what we're looking at, just some more graphics of where we're trying to see. You can see the different temperatures here when you look at the economizer where the heat's being removed, and then we go and then we would go into the catalyst bed, and depending on what type of catalyst it is and how much removal we need, you'll have different layers in that bed for the catalyst. And then next it's going to pop up a picture of a Yokogawa pressure transmitter, I think. Ed, Bob, if you'll move forward. And basically, Yokogawa, I'm here talking about our laser analysis, but we have multiple field instruments as well that can be used on these systems. Next, please. Okay, next. So one thing that's quite interesting, and why, and not everybody's using ammonia slip analyzers, but one of the major benefits of making this slip measurement is that we've seen over the years that as the catalyst is exposed to the flue gas, and there are different contaminants in the flue gas, sulfurs, other heavy elements, metals, that will actually contaminate the catalyst and cause it to become less active or reactive. And what you'll see is it takes more ammonia to actually achieve the same NOx level as the catalyst gets older. And this could be years. This usually is years for this decrease to take place, but we've seen in many instances as the catalyst life gets older, you're going to start seeing that injection rate has to be increased, and we see additional slip, and to keep the NOx at the same level that you had seen previously. And we've actually had some customers tell us that the ammonia slip allows them to predict the end of life of the catalyst, and that's very useful because these catalysts are very expensive and often have very long lead times, and they cannot operate the facility without this unit working properly. And so ammonia slip, it says right there, it basically is the best indicator to show you what this curve looks like, and we can actually predict the end of life. Next, please.
And so basically the utility is going to be able to see the deterioration of catalyst activity and be able to make plans for replacement.
Yes.
More specifically and timely manner than they would otherwise.
That is correct. Yeah. If you don't know what the slip is, it's going to be very difficult to be able to predict that just based on injection rates of the ammonia reagent. Yeah. Okay. Another thing that we've noticed, and this is probably more critical in coal fire, but it is important in any gas-fired system. If you over-inject ammonia, first thing you're going to do is it's increased cost of operation, and it may not be significant short-term, but long-term it will be significant. So we want to make sure that we're injecting the right amount of ammonia so we're not wasting it. Another thing is, if ammonia mixes with moisture, it can become corrosive, so you can have issues downstream of the SNCR or the SCR. That you can have corrosion on all the metal parts, and then of course we also don't want to have excess ammonia going out the stack. If you have sulfur in your fuel, it's very common to have sodium bisulfate and ammonium bisulfate and bisulfate to form, which usually is a green crystalline type of substance, and it sticks to everything. And when you get into coal-fired plants, just to touch on that, I've actually seen situations where they can totally plug the preheater and shut the unit down. And that's something that you want to avoid if you're over-injecting and you have high sulfurs. But even in gas-fired, if you get a non-sweet type gas, you can have these deposits that can cause maintenance issues and shorten the life of your asset long term. So using an ammonia slip analyzer will allow you to make sure that you have that optimum slip, and you're running the unit where it needs to be run. Next. So one of the difficulties of controlling an SCR is actually getting a good ammonia number and a good NOx number for that matter, because especially after the injection of ammonia, when you try to make the measurement of NOx or ammonia extractively, you have to put a probe in the process. Then you have to pull the gas down the probe, even though it's a heated line typically, and these often can be 50 to 300 feet lines depending on where the analyzer shelter is. And when you have this situation, now I have NOx and ammonia in a stainless steel tube typically, and it basically has a lot of surface area, and the NOx and the ammonia continue to react as they go down the sample line to get to the analyzer. So now even if you have an analyzer that can make the measurement, it's not representative of the actual ammonia measurement in the process, and the NOx has been reacted as well. And then as the ammonia level goes up, the problem is compounded because you have more reagent in the sample to measure. Also, depending on, on some of these units, the geometry is quite big across the duct that you're trying to make the measurement on. And if you want, meaning the span, the outlet of the SCR or the NOx removal system is quite large. I've seen them. You see them anywhere from 6 feet across to 50 feet across, and if you only have a single point where you're pulling the gas out of the duct, it's just localized. You don't have a good understanding of what's happening from the stratification point across the duct, and you may have a high reading or a low reading. So controlling it is very difficult if you don't have a good quality number. Okay? Sorry, next. So, benefits of actually making an ammonia slip measurement. Well, first of all, regulatory agencies are cracking down on what you're allowed to put out the stack. We heard that this morning. So lower emissions of ammonia and hand in hand with lower NOx. And they said 2 parts NOx, 2 parts ammonia this morning. I heard that multiple times. So monitoring the ammonia actually benefits to make sure that we have the proper ammonia emissions. Another thing is if you over-inject, we've seen it where you can have deposits and plugging corrosion. Ammonia has an odor in itself. We reduce the reagent cost. I mean, it has a cost, and it adds up over time. Of course, the process improvements, efficiency, and then reduce catalyst cost. This really should be, it actually rolls right into the improvement of catalyst management, as we spoke about earlier. Basically, you can determine the end of life and you can schedule that outage appropriately. And another thing, if you really do, if you get way out of control and you have too much ammonia injection, you can actually, it does plume as it goes out the stack. And we know people don't like seeing anything visible coming out of the stack. Okay, next, sir. One more. Yeah, maybe one more. Okay. Next. So, as mentioned earlier, so basically when we go to extractive analyzers, which TDLS makes the measurement in the process, traditionally most analytical measurements are made extractively, and quite honestly, when it comes to continuous emission monitoring for the standard gases of oxygen, CO, CO2, SO2, SO3, those are still made, from a regulatory point of view, those are still made at the stack with an extractive sample handling conditions, sample lines, and that's what the regulatory agency wants to see. But those outside of the SO2, SO3, those are not reactive gases, and you're not controlling off of them, so the amount of time it takes to make the measurement is typically acceptable. But when you look at the ammonia measurement, it's actually a control point, and it can be an emissions point. So the analyzers, the TDLs that are out there, we make measurements in anywhere from 2 to 5 seconds, right in the process with no transport time. So if you go extractively, which is traditionally what you see, you have slow response time. That's an issue with control. Also, as we mentioned earlier, when you actually pull the sample out, you change it. So we change the gas when you go extractively, so it's very hard to get representative samples, especially with reactive gases. So leaving the in the process helps us with that. And then when you take the sample out, even with gas-fired, if you have any sulfurs or anything that's not clean, you have all of the components of the sample system you have to deal with, filters and chillers, and we don't have any of that. That was really helps with this as a long-term cost of ownership based on the maintenance, and then also the quality of the measurement using TDL versus traditional technologies. All right, next, sir. Another thing that we've had the privilege of participating in over the last year was EPRI. They've done several studies on ammonia slip, even starting back in the mid-1990s. But recently in 2012 they finished up a study specifically for ammonia slip, and they looked at multiple manufacturers, and they have and if you are a member of EPRI, I don't have it with me, I apologize, we can find the number of the document, and you have access to that. And basically they went through and they defined their test method, they defined their test apparatus, and we actually were allowed to send a technical person while they did the testing to make sure that the analyzer was set up properly, and witnessed the testing. And they wrote a very nice report, and they went through and published all the results. And Yokogawa had a very positive showing, and the results are very good for Yokogawa as far as accuracy, what temperatures the measurement was made at, and all the conditions. So I'm very very happy with the result of that, and I hope that most people that in the power industry are members of EPRI, and you should have access to that document. And it will compare other manufacturers to Yokogawa as well. Next, Bob. Okay. We'll move on to actually the analyzer and some brief benefits of the Yokogawa ammonia analyzer, which we do by basically the Yokogawa TruePeak TDLS 200. So here's a picture of it, and there are two sides, and it's basically we break it apart and we mount it on the process. I'll show you in a moment with flanges, and we shoot a laser beam through the process, and we look for the energy lost at a specific wavelength to measure the ammonia and the moisture if you so choose. So what's very nice about this is it's very precise to ammonia. We know the only thing that's even close to the measurement is moisture, and we can measure and correct for that. We do not have any sampling. The maintenance is very low as long as it's installed properly and we maintain the proper window purges. Basically, when we set this up and it's installed, the process does not come in contact with the analyzer. So now that removes a lot of the issues with maintenance, and we have very long life and very long maintenance intervals typically. We typically say our upper temperature is 1500 degrees C for the whole platform, but specifically for ammonia, we really operate around up to 450 degrees C. We can stretch that to 550, but we need to know ahead of time. And one of the big benefits that I alluded to earlier is that typically, traditionally, analytical measurements are made with a single probe in the process. And when you look at these larger geometry spaces where we're trying to get a representative sample, due to the flow dynamics, we sometimes have pockets inside of the duct that have different concentrations than we're actually making the measurement. So one thing that the laser allows us to do is shoot across the space, and it is a beam. I mean, it's about 20 millimeters in diameter. It's not a planar measurement, but it shoots across and dissects the process, and it gives us an average number of the ammonia that passes through the beam. So if you have highs and lows, there could be stratification. We're going to give you the average bulk number that's in the process, as opposed to a single localized point that could be very high or very low. Okay, next. So one really nice thing about laser technology in general, the signal processing is right. We really do pick areas where it is interference-free measurement. And if it's not interference-free, which this one is, it's very well defined, and we can typically deal with the background interferences. But in this one, there are no interferences. And this allows us to make very precise measurements. It allows us to also be very selective. Sorry, I apologize. It's very fast, relative. I mean, with no transport time, we just have the processing time, and we run it at 5 seconds typically. It can run faster, down to approximately 2 seconds, but the best measurement and noise rejection is at 5 seconds. So our lowest detectable limit is it says 0.15 ppm here. Now that is true, but realistically, our true accuracy is dependent on how far the beam travels, which means if you have very large ducts of gas-fired, the accuracy could be better. If you have a very short duct, This accuracy, this detection limit may be difficult for us to reach, but traditionally these are typically at least 6-foot ducts, and we can achieve this 0.15 ppm detection limit. And at 0 to 20 range, if you need to scale this to 10, we can do that, or if you need to go up into the hundreds, it can also be done. The dynamic range on the TDL is very wide. Another thing that's quite nice about the laser analysis, it's a direct measurement. We are looking at a specific wavelength. Ammonia absorbs the gas at that specific wavelength, and then we calculate, we use temperature, pressure, how far the beam traveled, and the signal from the analyzer to calculate concentration. Unlike some other, there are other methods out there to do it that are indirect, like a chemiluminescence or electrochemical, and even chemiluminescence, there are indirect measurements. So it's very nice that we are first principle measurement here. Another thing is that there are no moving parts in this system. It's fully, I apologize, it's just solid state. Also, I'll just highlight right here. The analyzer is full of diagnostics. If the laser beam does not reach the detector, you are immediately notified, and you know that the measurement is not working. That is a nice thing about having the positive indication of operation, because the beam continually travels through the process. And this is important because not so much on gas fire, because it's usually very clean. When you get into coal, we have to be a little more careful because the ash attenuates the beam, and we need to know what the ash level is, and then we can actually define how far the beam will travel through the process, and then we would work with you to adjust the geometry with tubes, or going across a corner, or picking a place where the path length is works for the amount of power that we have. The analyzer, so it's very full of diagnostics. It has onboard data acquisition, to where we collect about 2 weeks of spectral data. We collect the 4 to 20 data. It's also collected on the analyzer. You can actually get that off via Ethernet or a USB drive, and we can be interrogated in Excel. Very handy, especially for new users when we're trying to show them how to use the analyzer, but it's very simple to use. Okay. Oh, actually, Bob was sorry, back one, I apologize. There's one more interesting thing on that slide. On this bottom picture down here on the right side, you see the black pipe. That would be your process. Maybe it's 6 feet, maybe it's 40 feet. But the connection here, we use ANSI flanges, 2, 3, or 4-inch flanges. It's hard to see between the flange and the analyzer. There's a flexible bellows, which allows us to torque the flanges to pipe spec, and then we can steer the beam outside of the process, and allows us to do the alignment and then lock that in without with maintaining process integrity. All right, next. All right, some redundancy here, but basically no transport, fast response, no loss of components in the sample system. That is key for making a reliable, accurate measurement. And we don't have any filters or pumps or sample lines. We do have some purge lines that we purge the windows with to make sure we keep the process off of them, but other than that, it's very clean gases, and it doesn't have anything to do with transporting the sample. Sorry. So one other thing so basically another thing that we go to is, since we don't have to deal with the sample lines, they're not heated. We do have some purge lines, like I said earlier, but they're not going to be heated. There's nothing special about them. They're stainless steel. And then as far as lower installation cost, typically analyzers are put in analyzer shelters, and this hangs right out on the process. So there's no shelter required for this analyzer. Next. Just a picture, a good picture of one installed on a side of a duct here. Obviously, this is a coal plant, but it's similar to what you would see anywhere. This is going to be the detect side. It's the smaller of the two. This shows the analyzer itself. Then you move, and there's the the alignment mechanism, which is attached to the flange. This is very nice here. They actually have a spool piece between the analyzer and the process connection, and they have blowers to provide purge air to keep any of the process from coming in contact with the analyzer, and also to keep any blockage out of the nozzle so that we always have clear line of sight. And we would work with anybody who wanted to do this for your specific needs to make sure that we have the application proper for the fuel that you're burning. Okay, actually this is a picture of AEP. See here in Virginia.
Oh yeah, and that's a fairly good size installation, isn't it?
Yeah, we have there's nine of them there. It's a good installation, and they run less than 2 ppm almost continually.
And I guess that was one question I had. That's despite a fairly high particulate loading that you're over to overcome that interference by calibrating for a given level of particulate in the gas?
Yeah, so what happens is we have a certain amount of energy that the laser outputs, okay? And it's actually significant. It won't harm your eye, but it's significant. And so these were like 20 feet across, and I think we had to cut it down to like 12 feet. So we actually have steel tubes that go into the process on each side so that the laser only travels approximately 12 feet through the ash. And we can actually typically, if you tell us what the maximum dust loading is, we can calculate how far that beam will travel through the ash.
But so, it's not negatively affected by variations in the ash. It's as long as it doesn't exceed the amount that would prevent the beam from reaching the other side.
That is correct. There is so in a clean room, we start at 100% transmission. As long as we get 5% of that transmission back, that's where our alarm point is. The measurement is not affected. It's a sliding scale basically, but because of the way we make the measurement, it is not affected by that variation in energy coming back to the detector.
I'm glad you clarified that.
Yeah, you have to clarify. Yeah, that has to be clarified because you're right. That we call it transmission, but it's basically the amount of energy that hits the detector. It varies all the time in every application we go into. You have to be able to overcome that, or the reading would be worthless. Okay. Just an idea here. We have this question asked quite a bit. What about alignment? How do you keep the two sides aligned? And we basically have a spec that the nozzles have to be in the same plane, they have to be lined up, and they have to be within 2% of the center line between the two nozzles. And this is definitely a mechanical consideration that has to be taken when the installation is being done. Another thing that's important is that often when you go into most fired assets, the walls are not very sturdy. So there has to be considerations taken when you go to do the installation to make sure that the nozzles are firmed up and don't move when you have expansion and contraction due to temperature changes in the boiler itself, and then also environmental. We've had situations in some fired assets where everything's running great and you're open to the environment and a big rainstorm comes through and the wall will move. So we just have to work with the mechanical group to make sure they understand what the requirement is. And what we do is quite interesting. If you're under 18 feet, the beam is a collimated beam. It's only about 20 millimeters in diameter. If you go over 18 feet, we diverge the beam so that the beam spreads out. And we don't do that in coal-fired plants because you have to keep the beam very powerful. But when you have gas-fired, we can spread the beam out because there's not the dust consideration. And now when you spread the beam out at about, if you go to 60 feet, the beam is about 0.7 meters. So 20 inches in diameter or so, and now we have you have more tolerance for movement, and we still catch some of the beam. We can make the measurement. It's quite a nice feature. But most people ask about alignment. If they're installed properly with nice firm nozzles, and we get them aligned initially, there is some adjustment once or twice a year potentially due to vibration. But in general, alignment, the way we do this, the alignment holds very good, quite well. Okay? Okay. thank my colleague Ed Deck for this slide. But basically, there are more and more TDL technology-based analyzers being used every year in power, in petrochemical, in refining, for power, for combustion control, for process safety. The technology is being accepted more and more every year. There are more and more people being involved in it. It is a very solid measurement technique. One thing that we run into in America, maybe not so much these days, but we do run into some situations, is that Yokogawa sometimes gets some resistance because it's the parent companies in Japan. But I will tell you that this product is built in 2 locations in the United States, in Georgia, Noonan, Georgia, right outside of Atlanta, and in Houston, Texas. And I do not foresee that changing anytime in the near future. The support comes out of the U.S., the engineering, the research and development, we handle all of that direction from the U.S., and it was developed right here with the backing of U.S. companies. We have done, we've done in excess, it doesn't sound like a lot, but we've done in excess of 50 to 60 units in ammonia, and it ranges from gas-fired for utility boilers, coal-fired utility boilers, gas-fired boilers and assets, and petrochemical and refining. We've spanned all of that. And then, so we have experience, and we have experience from years ago using a different manufacturer. Another nice thing that we run into when you start talking about laser analyzers is many of them, you can't do anything to them. If you have a failure in the field for some reason, many of them have to be returned to their respective repair facilities. We designed the TruePeak to be every part in the analyzer can be repaired by a qualified technician in the field. And that can be our technician, that can be the user's technician. But that was done on purpose. And that's one reason why it's a little larger than some. Also, we have a SIL assessment done for safety. And this is basically for safety shutdown systems. It may not be as critical for an ammonia slip measurement, but it should allow us to leverage so that people can understand the quality of the analyzer and the fact that it has very good runtime data and very good quality components, because when you start talking about safety integrated, limits, they do a lot of research to make sure that all the components have very low failure rates, and we made sure that the TDL meets that. And then we have our validation. Because we're in situ, you cannot do the zero. We have a standard addition method that we followed that was based on a procedure, validation guidelines that we picked up from the EPA as well. So we try to do everything right so that everybody can meet their requirements. Okay, next. And we're almost done, Bob. I actually hit this slide on the one but basically what you need to look for is some things that can help you when you're thinking about your financial decision to move toward ammonia slip analyzers. If you can determine the end of life of your catalyst and schedule your outage properly, I can't put a dollar amount on that, but somebody in organizations can. I think that's pretty critical. And then also, when you start getting your loss of activity on your catalyst, it's nice to know how much ammonia is actually slipping through. There's a dollar value attached to that. And then, of course, you got to make sure you're meeting your NOx reduction, and there's also requirements. Excuse me. All right, next. So basically, Yokogawa is here. We have a nice, a very good offering for TDLS for making ammonia measurements, and there's multiple reasons in multiple places depending on your applications. And we have some pretty good references in the field, and we have good experience as well. So Bob, that's all I have today.
Yeah, I had a couple questions. One, you know, this moisture interference, and you're saying you can adjust for it. Does this mean that you should try to say seek exceptions, which I believe some of the monitor companies have done in the past for certain things, where a particular agency would allow, say, an in-situ more appropriately if you could demonstrate accurate moisture compensation?
Yeah. Okay. So moisture doesn't interfere with ammonia unless we get to lower temperatures, and where the SCRs operate, the temperatures are above that position, that point. So when we make a measurement of ammonia after SCR, SNCR, there is no overlap, so there is no moisture interference. But what I was saying is that when you get to regulatory agencies, today the way that most permits are written, the measurements of O2, CO, CO2, NOx, SOx, they're written to where it's a dry measurement, where the moisture, the condensables, the moisture has been removed, basically at a dew point of 4 degrees C. And what happens is when we get into the in situ measurement, we cannot remove the moisture. The nice thing about the ammonia analyzer is we can measure the moisture and we measure the ammonia, and if you want us to report on a dry basis so that your regulatory agency, it meets the same requirement as the other constituents that are being measured, we can actually do the compensation inside the analyzer to report both the wet measurement and their volume, right? Their volume measurements. We can report the wet measurement and we can report the dry measurement. And basically, the only difference between the two is you know, the volume adds up to 100%. The ammonia is 10 ppm. The moisture is 15%. We just subtract the moisture and we normalize it, and it basically gives you a higher ammonia reading. And that's what the utilities, the regulatory agencies are used to seeing as that dry measurement.
And they're willing to accept this calculation based on also measuring the moisture.
Right, we've done it. Yeah, we've done it. We don't do a whole lot of regulatory measurements yet, but we have done it. We've done it in California and we have done it in Texas, and we actually did it in Oman as well. So we've done it several times, and they did accept it.
There are several companies that are experimenting with the Yokogawa TDL on using it on an extractive basis, and I think one of their rationales was the ability to measure dry. But what you're saying is the accuracy by subtracting out the moisture in the gas should be equally good on an in situ basis.
Yeah, I think it may be better because you don't have any transport reactions taking place. But with that said, depending on where the company, if you make the measurement very close and you keep the sample lines hot and the flow rate is high, you're going to minimize all those reactions. The problem is when you start stretching the sample lines out and give enough residence time for the ammonia to react with the NOx, then you have an error in the reading. You are correct. When you go extractive, it's much easier for regulatory agencies to accept the current process for doing a zero and a span on a daily basis, and sometimes that's easier to do it that way than to try to overcome and do it a more accurate way.
So I guess we need an education of some of the regulatory agencies here, and as you point out, there's a rapidly trend for increasing use of the TDL, so right. There seems to be the impetus to do that.
Right. We just need to make sure when the users are looking at TDL, what are you using it for? Are you using it for control and monitoring the SCR? Are you using it for emissions? And maybe all of them, okay? And if it's emissions, then we got to make sure the permit meets the requirement.
And the fast response certainly means for control that the TDL is an ideal tool, is it not?
Yes. Yes, it is.
Well, Don, I'd like to thank you. It's been a very interesting presentation. I didn't realize you had as many as 50 ammonia analyzers out there, so you are definitely leading the field in this regard. And we'd like to learn more about some of those installations in the future, and would like to thank you for participating today and to putting up with some of the problems that we had with our webinar earlier today, and your willingness to get on this afternoon and finish the job. So thank you very much.
Thank you, Bob. It's been my privilege.
Okay, talk to you again. Bye now.
Bye.